but I'll start recording now. Okay, we'll see once I start using the whiteboard how to manage that. This is new for me a little bit. So welcome everybody to the new semester. Is maybe your first class, maybe your second or your third, maybe for some unfortunate people it could be your fourth class. So this is procesamiento masivo de datos. So this is big data, effectively, the course of big data. So today we're going to have a general introduction, and we are going to motivate a little bit the course, talk about why it's necessary, why it's interesting, a bit about the structure of the course, how we're going to organize the course, and so forth. Today I'm going to try to speak a little bit more slowly so you can get used to my Irish accent. And then maybe later I'll forget about it and I'll start talking really quickly like this. And no, I'll try not to. Okay. So, of course, if you want to ask questions or comment or anything, Spanish is perfectly fine. Yeah. So there's no problem in asking questions in Spanish. We're going to start with why we're here, what's the purpose of the course, and speak a little bit about the value of data. Yeah. So, to start by motivating the value of data, we're going to go back to 1854 to Soho in London. Does anyone know what was happening in Soho, London in 1854? No? Una playa, yeah, then? No, cholera. Cholera, see? So there was a plague of cholera in Soho in London in 1854. So at that time, not much was known about cholera compared to what we know now. So what do we know now about cholera? We know that it's an infectious and often fatal bacterial disease of the small intestine, typically contracted from infected water supplies and causing severe vomiting and diarrhea. So not nice, not pleasant. Yeah. What did we know then? Well, at that time, we didn't know about bacteria. Yeah. So we didn't know the causes of these kinds of illnesses. We didn't know that it was a disease of the small intestine, typically contracted from infected water supplies. So we just knew that it was infectious and that it would cause severe vomiting and diarrhea. Yeah. So this is what we knew in 1854. The theory at the time was this theory called miasma or miasma. What was this theory? It was basically that in built up areas, like in cities where lots of people were living together, that people would just spontaneously get sick. And that was just life. Yeah. So if you were living in a dirty big city, you would get sick, and people would get sick, and these things would happen. And it was something that built up in the air, some sort of dirt or contamination, which wasn't so far from the truth, maybe. But this was the theory at the time. So in 1854, the authorities in London were searching for the cause of this illness of cholera. They didn't understand bacteria and so forth. So they started looking in different areas and trying to figure out what could be causing this. How can we slow the spread down? And this physician, Dr. John Snow, had an important role in understanding the cholera outbreak. Yeah. So he lived from 1813 to 1858. I know what many of you are thinking. Not this guy. He did a survey of Soho, John Snow. So he basically went around and started collecting data. Yeah. So he started collecting data, all the data he could. He went visiting different places, asking who lived there, how many people lived there, how many people had gotten sick, where they worked, what were their daily routines, where did they get water from, who worked in what places, and so forth. Yeah. So he went around asking and collecting data about the inhabitants of Soho in a notebook. And what he found collecting the data afterwards, okay, this is another representation of the data that was later printed. What he found was the information you see here. Right. So what we see is a map, and we see these black rectangles. Okay. These represent, might be slightly difficult to see, but these represent cases. Yeah. So here it means that there's a lot of cases. Yeah. So these black bars somehow mean number of cases at that residence. Here in the middle, we see pump. Bomba de agua. Yeah. So people needed to go to these pumps to get water. Yeah. So what's interesting is that a lot of the cases seem to be somehow centered around this pump. What is this border here? This border is essentially a Voronoi diagram, or a style of Voronoi diagram. What does it mean? Basically, it's the region where this is the closest pump. If you're within those boundaries, yeah, that somehow that pump would be your closest water pump. So what was the conclusion without knowing anything about cholera or bacteria? Well, they knew about cholera, they knew, it from its symptoms. What could we say based on these data?
The water was the problem?
Yeah, we could say the water. It seems to be centered around this water pump, and maybe this water pump is the cause of the spread of the disease, right? So based on this, the hypothesis, the idea of John Snow was that this water pump was somehow causing a lot of the problems. Yep. And okay, here's another graphic, might be clearer to see. Here we see somehow a number of cases with larger circles, meaning more cases. And we see the blue icons here are the pumps, the bombas. Right, so we see that somehow a lot of the cases are centered here. Yeah, around this. So 616 deaths later, and 8 days later, John Snow convinced, based on the data he had collected, to remove the pump handle, right? To take the handle off the pump to make sure it was no longer usable. Yeah. And this showed a dramatic reduction in the number of new cases. So this is called the Broad Street pump, and you can go, if you're in Soho in London, you can go there. You can find a pump dedicated to John Snow. In 1854, that cholera is conveyed by water. Yeah. You can also go and take a selfie, post it on your social networks. So what was the finding? What was the hypothesis, and at least some strong evidence, maybe not confirmed at that point, but strong evidence to suggest that cholera is typically contracted from infected water supplies. Yeah. Still didn't know anything about bacteria or the causes, but at least now we know that it spreads in water. So this was very useful to help to avoid the spread of the disease. Yeah. So from that point onwards, what would happen is if there was an outbreak of cholera, they would put a notice on the streets, what was called a boil notice, to boil the water. So people would boil their water, and that would eliminate or greatly reduce the chance of contamination. Yeah, so they could still take their water, they would just boil it before they consume it. And this was very successful in dealing with cholera outbreaks in the future. Again, not this, Johnson. Okay. All of this 30 years before the discovery of the actual bacterium that causes cholera. Yeah? V. cholerae. So for this reason, John Snow is known as the father, the godfather, the grandfather, whatever you want to call it, of epidemiology. Do you know what epidemiology is? We all know lots more about epidemiology these days, right? We've all lived through epidemiology, the study of infectious diseases and how they spread. Yeah. The success stories of epidemiology include the eradication of smallpox, viruela, the near eradication of polio, the limitation, well, at least addressing malaria outbreaks, as well as various vaccination programs for various sorts of diseases. Yeah. This is largely a data-driven discipline. Yeah. Not just in epidemiology do we see the value or the importance of data, but we also see it for genetics. We see it for climatology. We see it for astronomy, for particle physics, for social sciences, social networks, for politics, for economics, and so forth. So these days, notebooks are no longer good enough, right? We're not writing data in paper notebooks anymore. We have new ways to address this. We've seen the rise of computation from electromagnetic devices, bombs, punch cards, magnetic tapes. And now we have the hard drive, and not just the hard drive, but we also have solid state disks. Yeah, so we even have one step beyond that. Yeah, so we can store massive amounts of data in these media. Any questions, comments? Nope. Okay, so we've seen a massive growth in data. You've all seen this. We're all aware, more or less, of the amount of data that's out there. I'll give you some examples, and I'll use Wikipedia as a unit of measure, because if I start talking about petabytes and terabytes, it doesn't make sense anymore, right? So I have some estimates. Some estimates are easy to get more up-to-date estimates for. Some are a little bit outdated. I couldn't find any more recent estimates. For English Wikipedia, we're going to work with 51 gigabytes of data for English Wikipedia, which is just the text. Yeah, it's the no edit history, okay, but it's in XML format for the markup, and it's uncompressed. Yeah, so 51 gigabytes of data, and we're going to call this a wiki. One wiki equals one Wikipedia. So what do we have here? We have Wikimedia Commons, which is essentially as well all of the media and images and videos. It hosts all of that you see on Wikipedia. Yeah, so if you see a small video, mostly images or maybe some audio, this is hosted on Wikimedia Commons. And we see that it's almost 500 wikis around the same time of the estimate. 24 terabytes of data. Twitter. How big is Twitter? How many Wikipedias a day are people writing on Twitter? So about 8 terabytes a day, 157 Wikipedias per day. And this is quite an outdated estimate. This is from 2013. Yeah. So this has gone up, right? So hundreds of Wikipedias a day are being written on Twitter about very interesting topics, I'm sure. Anybody know what this is? Yeah. Very good reading. Very good eyesight. Large synoptic sky survey telescope. Sorry, large synoptic survey telescope. Anyone here from astronomy or doing courses in astronomy? So there's a lot of big data used in astronomy. Actually, the astronomers are working with a lot of stuff that we will talk about in this course. So I'm co-supervising students working in the big data and astronomy. So this is LSST. Effectively, it's a huge camera, like astronomic camera, that's taking video of the night sky. Why taking video of the night sky? Because they want to notice when things change in the sky. They're looking for transitory objects or for things that change, for example, supernovae. So they don't want to look very deep into the night sky. They want to look broadly across the night sky and look for changes. Yeah. So it's taking a very high resolution video of the night sky. It's generating about 15 terabytes per day, or about 300 Wikipedias per day. Yeah. And I think that's just in terms of alerts. This is more notable detections. Facebook. How many Facebooks are being ingested, or how many Wikipedias are being ingested in Facebook? Facebook is ingesting around 600 terabytes per day, or about 11,000 Wikipedias per day. Yeah. So a lot of data on Facebook. Anyone know what this is? CERN, yeah. Large Hadron Collider. So this is processing about 1 petabyte of data per day, or generating about 20,000 wikis per day. And this is not just the raw detection data. This is somehow the filtered, interesting stuff. Yeah. So CERN has this massive data infrastructure for managing the collision data. NSA. Anyone remember what the name of the NSA surveillance program was? PRISM. Yep. So PRISM, of course, it's very hard to get estimates about this, but based on some back of the envelope calculations, based on what people knew, this was touching or observing somehow about 29 petabytes per day or about 500,000 Wikipedias per day were being somehow sent through the listeners of Prism looking for keywords detected relating to certain things. Google. This is 2014. This is the most recent estimate I could get from a reliable source. This is 100 petabytes per day, 2 million Wikipedias per day. It's likely to be a lot more already. And the internet, based on estimates for 2021, but from 2014, that we would reach 2.4 exabytes per day, or 47 million Wikipedias per day transferred. Of course, here we're also talking about a lot of video. Yeah, a large majority of this is video, right? And audio and so forth, multimedia. So what do we see? We see that today, data form a modern day bottleneck, that somehow we have all of these data coming in to our collection facilities or to wherever they have to be processed. And it's creating a bottleneck. The bottleneck is here, where we're trying to index or make sense or understand or analyze the data. Yeah, this is the slow part. We can capture, store, stream a massive quantity of data, but the hard part is somehow processing or making sense or making use of the data that are available. Yeah. So often when we talk about big data, we talk about some V's. Some people say originally there were 3 V's. Somebody found a 4th. Another person found a 5th, and people continue looking through the dictionary for words that start with V that could apply, right? But the 4 main ones, the ones that I think capture the challenges in the area, are the 4 V's here, which are volume. The size of the data is massive. Velocity, it means that the data are changing. You've got streams of data, right? It's not just one static file. In many cases, you have dynamic data. Variety, which means that you have to deal with data from multiple sources. It could be comments, it could be images, it could be video, it could be structured data, semi-structured data. And veracity, which speaks about the truth of the data. You have data that might not be reliable. You have data that you might not have high confidence in. Okay. So, any questions, doubts, comments? Okay, so just to give maybe some scenarios where one can see big data, and then we'll talk a little bit more about technical topics. Big data in action. Anyone here use Waze? Or maybe Google Maps, and yeah, a couple of users of Waze, right? So this idea is basically you have an app that tries to find you the fastest way to get home right now. Yeah, Google Maps can do something similar as well. So it's processing journeys, people moving through the city as background knowledge. It sees how different users are getting through the city, getting through different roads and routes. And based on that, they act as sensors, right? So if you're using Waze, you are a sensor because you're sending back your information to Waze, assuming you've given the privileges, yeah? So this is known as participatory sensing. And in many ways, many of you are, maybe all of you are in some sense involved in participatory sensing. Yeah, your apps that you're using are also taking data from you and using you as a sensor in the city, in the environment. Yeah. Getting elected president. So this started with Barack Obama and then became very much larger scale. The project Obama had was Narwhal, which was on Facebook. The idea was, how do we exploit social networks? How do we exploit data available on the web about voters in order to win an election? Yeah. So if I am a campaign manager, what do I want to know? What's the most important thing for me to identify about people? Who's the most important demographic to reach? They're called the undecideds. I don't want to talk to people who are already going to vote for me, and I don't want to talk to people who are definitely going to vote for the other guy, right? I want to find people who are still making up their mind or could be swayed to vote for me. Yeah. How could we do that? If we had access to Facebook profiles, right? We could start to classify and look at the data involved. We could look to see what interests people, what doesn't interest people. We can then send them targeted messages. We can send them messages that we think could sway them to vote for me rather than the other person. Yeah. So this started in a large scale way with the 2012 election. The project was called Narwhal. Very little was said about it, but of course it became a huge scandal later, which I'll talk about in a second. So the question is, who are the undecided voters and how can I convince them to vote for me? We can integrate profiles about people from different sources online and then send targeted messages. In fact, they were very scientific about this. They would ask if you were a proponent, if you were in favor of Barack Obama, they would ask, they had an app on Facebook that would ask to post on your behalf. And then they would post as you to your friends who were undecided. So in your name. And they had measured to at what point they would annoy people so much with this that people would stop voting or would vote for the other person. Right? They really had it down to a science, how to use or best use the social network to maximize votes. Of course, this became a big scandal later with Cambridge Analytica. There was an important difference in that Narwhal worked within the policies, the terms of service of Facebook. Cambridge Analytica didn't, right? It had this backdoor to all this other functionality. Okay. So some time ago, there was this application called IBM Watson. Have you heard of the game show Jeopardy from the US? So it gives you an answer of sorts, and you have to give a question that the answer is the question is the answer. So you have to give the answer, but phrase it as a question, right? So this says, with much gravity, this young fellow of Trinity became the Lucasian professor of mathematics in 1669. Any ideas? With much gravity? So the correct answer is Isaac Newton, right? So there's a hint. And we see that there's two human users and there's this automatic user called IBM Watson. So IBM Watson here has guessed the right answer, Isaac Newton, and we see the other answers and the probabilities it computed. These are two of the best human players of the game at all time, and we see that they're losing quite badly to this this AI. I mean, this is less impressive now. We're in the age of ChatGPT and all this sort of stuff, but this is at one stage was impressive. Yeah. So can a computer beat human experts at Jeopardy? Yes. And there is a big data, also a lot of machine learning involved in this. The one thing that was nice from a computer science perspective of building this was that they had a long history of questions and answers, or answers and questions from the show. So they could train models that were efficient for this. Yeah. They had a good training and test set. Surveying the night sky, LSST. What astronomical bodies are changing in the sky, right? So this is the question they want to answer, and it's surveying the visible sky each week. So it's surveying about 1/7 or so of the sky every night, and queries external catalogs for known information of the visible sky, I guess. Okay, so we've seen some scenarios, just some taster of different scenarios. There are many other scenarios we could talk about. In general, if we look at these applications and try to generalize something from them, what do we mean by data, right? So data can be semi-structured data. It can be relational databases. It can be JSON, which would be structured data, JSON, XML, CSV. It could be HTML forms. It could be HTML itself, right? Unstructured data, it could be text documents. It could be comments. It could be tweets. It could be whatever, right? Primarily text, and everything in between. Processing can involve data management, kind of indexing, querying, joins, aggregation. It can involve natural language processing, keyword search, topic extraction, entity identification or entity recognition, machine translation. It can involve data mining and statistics, pattern recognition, classification, regression, recommendations, or something else, or a mix, right? So there's many things that are kind of encapsulated within the big data sphere. In this course, I'm not going to talk too much about machine learning side of big data. Yeah. So it's because you need a completely different type of architecture and a completely different type of processing with GPUs and so forth to be able to apply machine learning at very large scale. We're going to be focused on data management, a little bit of natural language processing, and other such processing. So where to start? We've talked about so many things, and there's so much that so everything it's massive scale, very dynamic data. Processing can be anything. Anyone can do anything in any application. So how do we start to teach the course, right? To structure the course. I don't really remember where to start. I think it might have been on the right side, but I don't. I'll leave that as an exercise. Okay, so scale is a common factor. Scale is the essential characteristic of what we're dealing with in this course. We have a massive amount of data. So let's take a question. I have an algorithm. I have a machine that can process 1,000 input items per hour. Yeah. If I buy a machine that is n times as powerful, how many input items can I process in an hour? So it's a key question of scalability, right? So I have an algorithm. I have a machine. This could be the machine. This machine can process 1,000 users, 1,000 purchase requests, 1,000 emails classified as spam or no, whatever the thing is, right? So this can process 1,000 things an hour, requests. I buy a machine that is n times as powerful, 5 times as powerful than this machine. How many items can the new machine process? Does anybody want to guess n,000? Will it always apply in the case? Will it always be n,000? Is there something in the question? Am I cheating you of information that you need?
The problem is how the 1,000 input is managed by the algorithm. And the machine doesn't necessarily scale that.
So you say it depends on what the algorithm is. Yeah. How optimized it is. We can generalize even beyond that. Yeah, but it's basically how efficient is the algorithm. Yeah. So many of you, actually, let's see a quick show of hands. How many are from DSC, from computación? How many from Industria? 1, 2. Okay, Eléctrica? 6, 7. Okay. So we'll see a little bit of things that probably you've seen in computation, but maybe not in others. But I'll explain a bit the idea. So correct me as well if you've seen it. People from Industria and Eléctrica, this sort of notation of ON squared. I guess not. You ever seen it in yeah. So what we have here is a description of the scalability of the algorithm. Yeah, it's essentially how long it takes the algorithm to process n items. So in this case here, we have the graph for a linear scalability, linear scale algorithm. Yeah. So in this case, if we just read each item independently and just, let's say, for example, a spam filter. Yeah, we just read the email and we just get rid of it. We don't need to confer with all the other stuff. If we're processing each item really one by one, then this is the sort of behavior we can expect. So if I have a machine that's n times as powerful, I can process n times as many inputs. Yeah. So there's an O here, which means that it's asymptotic to the trend, but in general, it just means this is the general behavior of the algorithm. Here we have it for ON squared, which means that if I double, for example, the amount of inputs it will take, asymptotically, we could say maybe 4 times as much, 2 to the power of 2. Yeah. If I have 3 times the size, 3 times the number of inputs, I would need a machine that's 9 times as powerful to achieve a 3 times speed up. Yeah. So what does it mean if I have something that's n times as powerful? Well, let's say if it were 2 times as powerful, I was processing 1,000. With this machine, I get a machine that's twice. My algorithm is quadratic. It's about 1,414, whatever the root 2 would be. Root 2, 1,000. And so on. So this is cubic. This is to the 4. And this is, what's this called? People from computation, 2 to the n? Exponential. Yeah. So if it's exponential and I'm already processing 1,000 units, then adding even a machine that's 10 times as powerful makes hardly any difference. Yeah. Okay. So when we talk about big data, often algorithms that are quadratic, n to 2, are too expensive. There's just no hope. In some cases, your boss might come and say, I need to process all of these data and I want to do, I don't know, some sort of NP complete problem over them. In that case, you just say, sorry, no. So what do you do in that case? If you have an algorithm that's too costly, you have some options. Work with a sample. Can you reduce the size of the data? Work with approximations. There are plenty of good approximations that are quite cheap for difficult problems, right? But in general, you need to find some sort of solution that's not just brute force this algorithm on top of massive data. So in big data circles, we'll often work in the sphere of ON or ON log n. And quadratic is already too much. Okay. Just to note that this is not the same machine here. The reason why this line is so flat for exponential is that if we could process quite a lot of items, like 1,000 items already per hour, it's already a very powerful machine. Yeah. So this, if you were to draw this back, you can imagine how far back this goes, right? So it's somehow, these are not all centered at 0. Yeah, so this is not necessarily the same machine here. Questions? Okay, so when dealing with scale, we have to consider what's the cost of the algorithm that we're running. So here the question is, the question to respond to the question is, what is the algorithm, right? What kind of algorithm are we running? Another question, is it better to have one machine that's n times as powerful, or is it better to have n machines that are equally as powerful? N machines? Why n machines, or why one machine? Sometimes we use one machine. Sometimes we use n machines. Where do we use one machine? Where the scenario is complex. Yeah. So one machine works well where we don't have that much data, but the question is complex. For example, if we wanted to have a really powerful computer for doing climate simulations, for predicting chaotic systems, maybe for doing chess games, although that's kind of changed now towards more machine learning and so forth. But where we have a small amount of data and we need to look at all these different scenarios where we need a lot of threads and coordination. Yeah. N machines, this is, there are different factors involved. N machines that are equally as powerful are often used for applying relatively simple algorithms on very large data. Yeah. And it's mainly a question of economics. It's mainly a question that it's easier to scale this sort of thing here, because if we want twice as much, what do? We buy another N machines. Yeah. In this case, we can't really scale this sort of architecture very easily, right? We can't just buy double the amount of stuff and cram it in the same box. So in general, having multiple machines allows for scaling the capacity more easily. So we can look at two different groups of computation. We have data intensive, which involves applying inexpensive algorithms over very large inputs. And this is the sort of thing that Google and Facebook and Twitter are doing a lot. Yeah. Okay. And then we have the more compute intensive sort of applications. So this is where we have more expensive algorithms and smaller inputs. So there we have climate simulations, chess games, different types of combinatorial problems and so forth, which also use the N machine more and more, but traditionally they would have used more supercomputers, crays, and so forth. Okay. So largely we're going to be talking in this course about data intensive processing. So we're going to be applying relatively simple algorithms on very large amounts of data. And we're going to see how to do that. Yeah. So again, there's no black and white. We could use N computers for compute intensive. We could use a supercomputer for data intensive processing, but these are kind of general trends. Any questions or doubts? Nope. Okay. So distributed computing. The core of big data really is distributed computing. This is the one topic that we can say really unifies the area of big data. This idea that we're going to need several machines to address this task. Yeah. So we could also call this course a distributed processing of data course, for example. Yeah. So a core topic in this course is this idea of using multiple machines to process data. enabling what's called horizontal scale, where we add more machines. So this was Google in 1998. This was their hardware that they had. This was when they were starting out. Even then, they realized the importance of having multiple machines. I think they have about 5 here. They have 4 monitors, and they have a RAID storage, basically hard disks in a case that they built out of Lego. Yeah, so this was Google in 1998. Now Google is very different. We have these massive server farms, thousands upon thousands of machines in each, and so. But it's the same idea. So when we talk about distribution, we have to talk about data transport costs. The key problem, the first problem we have to solve is on the level of hardware. Yeah. And it's a question of how we can get data into a CPU or a GPU, although I don't talk so much about GPUs, to be processed. Yeah. So where will the data be stored? The data could be stored in main memory. It could be stored in a solid state disk. It could be stored in a traditional hard disk. It could be stored on a different machine over a network. That could be on the same rack, or it could be on a different rack. So what's a rack? Let me go back here. I have a useful image. These cabinets here, they will have what's called a rack switch. So there you have a cabinet like this, and you have a bunch of machines in that cabinet. And for each cabinet, or maybe there's 2 per cabinet or whatever, but there's going to be a switch called essentially a hub of communication just for that cabinet. So when we say a rack, we mean a bunch of machines that are close together. Yeah. So we have in the same rack or across different racks. So we have a CPU. And what we want to talk about now is the cost of getting data from storage to a CPU. Yeah. So we have main memory. We can talk about streaming about 30 gigabytes per second from RAM. And this can vary depending on the exact hardware. I'm going to give some ideas. The orders of magnitude are more important, but 30 gigabytes per second from main memory into CPU. Solid state disk does pretty well. Not nearly as efficient, but we could do maybe, actually this could change quite a bit because solid state disks are still developing, but 600 megabytes per second, for example. A hard disk, around 100 megabytes per second. And for network, depends on the type of network. There's all sorts of networks. This would be 10 gigabit Ethernet, I guess, 1.25 gigabytes per second. And we have network across racks, about 5 gigabytes per second. Now, there's something I have to mention, an important exception or something to keep in mind. But for the moment, we see that essentially the worst bottleneck here is a hard disk. Yeah, which is a problem. Why do hard disks exist then? Why do we have hard disks? Price, yeah, economics. Yeah, for storage, it's a lot cheaper. Also, with hard disk and solid state disk, persistence. Yeah, if the machine gets turned off, it'll actually remember the memory. Yeah, this is volatile memory here, RAM. So in terms of latency, we don't only care about how fast we can stream data. We also care about how long it takes for us once we send a request to get the data that we want, especially if we have lots of random access. We're not just reading something sequentially, but we're doing a lot of lookups for different locations. So we have main memory in the order of 100 nanoseconds, solid state disk, 10 to 100 microseconds, hard disk, milliseconds, 5 to around 10 milliseconds, network, around 500 nanoseconds maybe, and across racks, 1 to 15 microseconds. So you all understand the difference between bandwidth and latency? Bandwidth being the amount of data we can send, and latency is the delay when I send the request, how long for something to come back. Yeah. Okay. So what we see is that the hard disk is really bad. Yeah. We see that we can transfer 100 megabytes. Okay. And here we can do 30 gigabytes. So we can stream data from RAM about 300 times faster than from a hard disk. Yeah. Solid state disk is a bit better, but it's still nowhere near as good as having data in main memory, what I call main memory or RAM. Yeah. The latencies as well So we're going from orders and orders of magnitude, right? So we have nanoseconds, and there's 1,000 nanoseconds in a microsecond, right? And there's 1,000 microseconds in a millisecond, and there's 1,000 milliseconds in a second. Yeah, so we see the major gaps here. Why do I care? Why do I care if something takes me 5 milliseconds or 50 nanoseconds? I'm not going to know the difference. Yeah. So if we're doing a lot of requests, right? So if I look at the times, I'd say, I don't care. But if you calculate it in terms of how many requests I can do, then you see that there's orders of magnitude. Yeah, you can do so many more requests per second with this, or random access per second. Okay, so I mentioned that there's one small problem, which is that the network is not so simple in particular. Why? Because you don't actually store anything on a network, right? What's on the other side of the network? It's another machine. And where's it stored in that other machine? Sorry. Hopefully, or in main memory. Yeah. So it must be stored in one of these three, right? So really the network is additive. Yeah, it adds to something else, whatever is on the other side. So what we have is that it is important to minimize the network overhead. Also, the network is shared. So it's shared across multiple machines. The network gives additional cost to the other storage. And the network is shared across many machines. So it's a limited resource. Okay, so we need to think also carefully about where to put what data. So another little exercise, I have 4 machines to run a website. I have 10 million users. I'm not that successful, only 10 million. Each user has personal profile data, photos, friends, and games. How should I split the data up over the machines? Any ideas? Yeah, so more use, better access. But let's say, for example, would you, where would you put each of the elements of the application? Would you copy, let's say, all of the data onto all 4 machines? No. You divide the work. Yeah.
Haber leído de que generalmente se hace como una duplicación de la data, entonces como que creamos que se trabaja con 2.
Yeah.
Las otras 2 tienen exactamente la misma data para evitar problemas, y entre esos 2 pares hay como divisiones entre ellas y se comparten información.
Yeah, so it's very common in these sorts of applications to duplicate data, which sounds like you're wasting data, but you want to be sure that your application stays running. We'll get back to that. So that's a little bit more advanced than where we are, but we're going to assume for now there's no faults, which is a terrible idea, but we're going to assume for the moment that there's no faults. Yeah, and we'll get back to replication, to duplication a little bit later. Yeah. So I have 4 machines. I assume that they're excellent machines. They're never going to fail me. I have users, and each user has profile data, photos, friends, and games. I'm wondering, I'd like to use the whiteboard, but I'll try to do it on the slide. Let's see how this goes. If not, I'm sorry, people online, I'll try to share this. But any ideas? I don't think there's a good whiteboard space anyways, because if I do it here, you're not going to see. And if I do over there, I'll try it on the screen. So suggestions. So we're going to divide the work. So we're not going to copy everything onto every machine. So we have to decide on what's called a partitioning. So where is, I haven't used this in so long. No, I need to do this in, yeah. Okay. So how would we divide the work over the machines? There's 2 main options we can consider. Bad idea is also very welcome. Yeah. Okay, perfect. So we're going to put 2.5 million users on every machine somehow. We're going to do it randomly, but we're going to do it so that it's even, right? So 2.5 million. I'm not going to do this very much, so sorry. ... Option one, right? So we have 2.5 million users on every machine. Yeah. On this machine here, 2.5 million users on this machine here, and this machine here, and this machine here. What would be another option?
Display the categories.
Yeah, perfect. So let's say we would put the data here, profile data. I don't know. Profile. I'm not going to start drawing things. No. Photos. Okay, I started drawing things, which is a terrible idea. Friends and games. Games, I don't know, I'm just going to do a football. So we can split the data like this. Yeah, so we have partition not based on users, but on purpose. So let's talk about advantages and disadvantages of both. What would you say are the advantages of splitting it by user? Yeah. Yeah. So that concept is called load balancing. It's this idea that maybe, for example, the games are not so popular, or maybe it's that the games use a lot of CPU, but they don't use any data, right? So maybe we have an unequal use of the machines. Some machines are overloaded in their CPU, the disk isn't being used in another machine, and so forth. Yeah. What's an advantage? What's maybe an advantage of this way of dividing the responsibility? Yeah, so you know, if you're looking for the photos or if you're looking for the games or whatever, you know what machine to ask, right? There's a couple of other advantages that maybe. Okay, so maybe if as we grow, maybe instead of having one machine for each, we maybe have 4 machines specialized for games and maybe 20 for profiles, and maybe the ones for games have good CPUs, GPUs, whatever, right? But at this scale, I would say the better option right now is for the users, right? We're going to divide everything equally by users. Yeah. What's the advantage of having everything divided by users? Better load balancing, right? The flip of the negative for the other one. Will load balancing be perfect? Not exactly, but it should be much better. It depends on what the skew of user usage and followers and so forth would be, but we would expect it to be much better. Other advantages of this partitioning. Yeah, exactly. So if we really regularly want to get all of the data about one user, we just have to ask one machine rather than 4. Yeah. So it depends on the application, a little bit. If we have one page that has all 4 things, having all the information about that user on one machine would be good. So your idea was to distribute randomly, right? Does it have to be random? What's the disadvantage of random? So if we want the information for a given user, we'd have to ask the 4 machines. Maybe we could use something a bit silly would be use the letter of their first name or something, right? Well, we can get that more advanced and take a hash code of their name and take some modulo number or something, right? To deterministically find a number between 1 and 4. And given that same information for the query, we can find the machine. We just have to ask one machine. Yeah. So these sorts of concepts are kind of important. We're going to be talking a bit about these ideas later in the course. Yeah. Okay. So there are advantages and disadvantages to different types of distribution, but some general principles and design choices apply. So what I'd like you to understand are the advantages and disadvantages of different options, yeah, to be able to reason about them and then apply those to a particular application. So somebody mentioned about the replication, yeah, that it's important to replicate. So what is this idea? Basically, in a distributed system, my notebook here is falling apart due to heavy use or intermittent heavy use. A machine should last for about 10 years, or a hard disk has an average life of 10 years. Yeah. What happens if I have 3,650 hard drives that have been in operation for some time, right? So I have 3,650 hard drives. How often will a hard drive fail? So 3,650 days in 10 years. So it will be more than 50%. It's about 61% or something. Yeah. So if I have a large amount of hard drives, even if each of them has a very long life expectancy, it's very likely that they will start to fail and that there will be machines or hard disks failing every day. So we need to think about failures. So going back to our application, we have 10 million users. One of our machines fails. Yeah. And we spoke about two different distribution options. In the first distribution option, what are we going to lose? The ones where we divide by users. Yeah, we're going to lose all the data about 1/4 of our users. So those quarter of users are going to be very annoyed. The other 3/4 don't really care. They'll be very happy. In the other one, we're dividing by function. Yeah, profile on one, games on one, and so forth. What do we lose in that? We lose one functionality for all of the users. So everybody is annoyed, but not really, really, super annoyed. So which is better, which is worse? Well, it would be better to avoid the situation in the first place, no? So when we think about distribution, we have to think about the possibility that machines can fail either for a short time or for a longer time. So we need to decide how to split the data up over the machines. How to do this, again, depends on the application, but essentially what we're going to be applying is a replication factor. So a replication factor means that we're going to duplicate the data about every user in multiple machines. Yeah, so if one machine fails, we still have copies. Somebody mentioned about 2, it's actually better to have 3 copies. Well, it's obviously better to have 3 copies, right? But there's a particular reason why 3 is a more common number of replications than 2 that we'll get to. But the hint is that if the 2 of the machines disagree, you don't know which one is correct. So if there's one error, we'll get back to that. We're going into later class territory. So it's a bit like human distributed computation. Yeah, if there's maybe one person in the office who knows how to do a critical part of the business and they get sick, maybe they come down with cholera or something, that's not good for your business, right? So you need to distribute or have some sort of redundancy in responsibilities and separation. So distribution, again, is not always applicable. As I mentioned, there are certain things that are just too expensive to run on massive amounts of data. There are things in computer science that are provably impossible, and that's life. Yeah. So distributed systems can be complex to manage. They do come at a cost. They're not a one size fits all. They're not going to solve all of computing's problems, right? Some things we can distribute, some things we cannot. Even if we can distribute something, it can be complex to do so. So we have multiple machines that we need to take care of that might be in different locations. We have logs and messages in different places, different users with different priorities, different networks. We need to think about load balancing. We need to handle failures. Another aspect that is quite challenging in this course that you're going to get a taste of, and that was a difficult part, for example, of my PhD, where I was trying to work with lots of data, is that it's not like in other scenarios where you can just run something and see if it works. And if it doesn't, if there's an error, check it, debug it, fix it, try it again. In this, it's more, if you have an error in your code, you launch it on the cluster. 4 days later, you notice that there's an error. You see what the error was about. You try to fix it. You try to find in the data where the error could have occurred. It's in the second petabyte of the data. You figure out where that is. You go back, you fix your code, you run it again. You wait 5 days this time, progress. It fails again. Yeah. So this can be a difficult process, but there are ways to manage this, right? There are ways you can test on testing is very important. The good news is that there's a bunch of frameworks and abstractions that can help us. Yeah, so we don't have to do everything from scratch. So we have distributed processing frameworks like Hadoop, we have Apache Pig, we have Spark, we have Kafka, and we have distributed storage, also known, typically these would be essentially NoSQL stores. Yeah, so we have HBase a little bit out of fashion, Cassandra more in fashion, MongoDB. Maybe have people here used MongoDB? Yeah, a couple. Cassandra? No? Solar, Neo4j, Elasticsearch? Yeah, That's good. Okay, you're in the right course. So we'll see these in the course later, right? So we're going to look at these abstractions. Okay. Any questions? Doubts? Okay. So I'm going to talk a little bit about the implementation of Twitter. Unfortunately, there's information from 2013. There's newer information from 2017 that I'll mention, but nobody really has a clue what's going on now because Elon Musk has gutted the place. So half the people are gone and so forth. But there's some really interesting insights. So this is from the lead architect of Twitter who explained everything, which is really rare for this sort of company to do. So that's why I still think it's interesting to discuss. So it's an implementation of Twitter and it's a timeline. So how many people here use Twitter? Some people are very shy to, it's okay, the recording's not looking. I also use Twitter a little bit. So a timeline in Twitter, for those who don't know Twitter, is essentially a list of all the tweets, the notifications, the things that you should see because you're following people and they've tweeted or whatever. Maybe someone in your network has liked something or retweeted something. So these are the timelines. So in Twitter, at this time, they had 150 million active worldwide users, 400 million tweets written per day, 300,000 queries per second for user timelines. It means lots of people pressing refresh on Twitter to see the latest tweets. 6,000 queries per second for custom search. Custom search being where you type a keyword search to look for, I don't know, like I use Twitter for searching if there was really an earthquake or not. Like typing in temblor, terremoto, see what's going on, or if I'm just imagining it. So this is more or less what's facing us, right? We have to now implement a solution to host Twitter with this. What is the main aspect here we need to optimize in terms of queries? So we have two types of queries. We have queries for timelines and we have queries for custom search, right? Which is more important? The timelines, right? Okay. So what about the writes? Here we see we have the number of writes. We have about 5,000 tweets per second mean. And okay, when the Super Bowl is on and somebody scores 150,000 tweets, yeah, it's bursty, but okay. So we see that of all the things we see here, the thing we really need to optimize for is the timelines. Yeah, so it means what we need is what's called a read optimized solution. We need to be able to read timelines very quickly. It doesn't matter if the writes, because there's so fewer, 60 times fewer tweets sent than requests for timelines. That can be a little bit slower, or it can be maybe a little bit less efficient. So which aspect is the most important to optimize? It's the search for the timelines. So Twitter does something very strange, something that if you did databases and you suggested this, your professor would kick you out of the course. What they do is when you write a tweet, when somebody sends a tweet, yeah, there's basically two options. And the second one seems ridiculous. The first option is that you write it to the database, the tweet that was sent, and you associate it with the sender. Yeah, so you write in the database once, Aiden sent this tweet. What's the second option? Anybody crazy enough to come up with the second option?
You write in the database 3 times.
Yeah, so you write it, you repeat it in the database for everybody who should receive it. Yeah, so you find all my followers and then you write it in their timelines. So basically you're maintaining not what tweets were sent, but what tweets should be received. So you maintain always up to date the timelines of everybody. So if I have 1,000 followers, I don't have 1,000 followers. If I had 1,000 followers, my tweet gets written 1,000 times. And in databases, this is just a nightmare, right? This isn't even, it's probably still first normal form, but we're taught not to have repetition. So we'll write it for all of the people who should receive it. Why would we do that? It seems like a crazy overhead. Because the timelines then will be ready to go, right? We'll have the timelines perfectly organized, and when someone asks for it, when somebody asks for it, it'll be ready. So this is all hosted on Redis, which is an NoSQL store. And essentially we have here timeline, which is a list of all the tweets that a user should see when they query for their timeline. Yeah, so we're actually updating several times. So we get some ID of the tweet, the ID of the user who sent it, some control bits to indicate if it was a retweet or if it was something else. And if it was a retweet or in a reply to a tweet, what the original tweet was. Yeah. So this causes some issues, right? So it means that when these followers, this is from the list from the presentation, tweet, sorry, we're going to have to write something 31 million times. So when Lady Gaga takes a photo of her breakfast and tweets it or whatever, that causes 31 million writes to the Twitter. I assume they must have some special treatment for people with large numbers of followers. Okay, but in any case, what this helps with is when we go to query timelines, we can manage this sort of workload of 300,000 queries per second. And the times that they report would be 1 millisecond at the 50th percentile, 1 millisecond median case, and 4 milliseconds in the 99th percentile. Right? So this is the time, how long it takes. So we can do it in 1 to 4 or 5 milliseconds. Okay, so this is the service timeline. Then there's GizmoDuck and TweetyPie, which are related services that allow for enriching, for essentially for taking the tweet ID and getting the text back, which is not stored in the timeline. And also TweetyPie, which allows for seeing the user's social network, for seeing who they're connected to and so forth. And they're used to populate the timeline together. In terms of text search, when I search for terremoto or temblor, this goes in a different direction. So what happens here is that we have to use a different set of technologies for that. We use inverted indexes. If you haven't heard of those, we'll see those in the course. We use Lucene, a Lucene clone, which is called Earlybird, which is an implementation of inverted indexes. And we're going to write once. And we're going to query many times. So what does that mean? In the case of the timelines, it's query once. It's write many and query once. Yeah. So write many, read once. And in this case, we're going to write once and read many. So we're going to index different tweets in different locations. And then we're going to ask all those locations what tweets they have that are relevant for the query. So to illustrate the difference, here we have the pipeline if we have timelines. So when we get a request to write a tweet, we have to write it to multiple places in Redis, multiple timelines, all the timelines that are interested in this new tweet. Yeah. But then when we read, we just have to read from one location. Yeah, we have a specific place where we know that the timeline of a particular user is. In the other case, when we're writing for indexing for text, for doing text search or keyword search, we write to one place, just anywhere, any of the locations we have available. And then when we read, we query all of those, right? So why do we apply two different behaviors? Essentially here, we apply a very non-traditional type of behavior, which is the write many behavior, because we have quite few writes compared to the number of reads. Yeah, so we have on average 60 times more reads than writes. Here, it's more or less the same. Yeah, so we don't really need to optimize the reads so much over the writes. So this is what we'd call read optimized, and this is more traditional write optimized flow. So in the full architecture for Twitter, we have 3 elements. We have a part for text search, or sorry, 4 elements. We have a part for text search. That's where somebody types in a keyword search, and this uses one set of technologies. We have another component here, which is for timelines, which uses NoSQL. We have another component here, which is for mobiles. So if you wanted to use mobile apps or you have a subscription and you want to get notifications, there's another push component here. And we have a batch compute. What does batch compute mean in the context of Twitter? You'll see trending topics. You'll see topics that are super common, right? So somehow they need to aggregate across all of the tweets. What are the things that are most mentioned? Yeah. So across all of the tweets in Twitter, batch compute, essentially it takes all those tweets and distills them down into a list of trending topics or a list of interesting keywords or hashes. Yeah. Any questions? So in this course, we're going to be dealing with the three of these aspects, we're going to be starting actually with the batch compute. We're going to be talking about things like Hadoop, Spark. Has anybody used Kafka? Any of these? No? Then we're going to be talking more about the text and keyword search. We're going to be talking about search engines, indexing of text, how to implement keyword at very large scale, distributed on machines. We're going to be using in the lab as well a system called Elasticsearch. If anyone has used it, no? That's good. Then we're going to look at NoSQL, which is this component here. Yeah. So we're going to be looking in the labs at Cassandra, MongoDB, and Neo4j. Yep. Any questions or doubts? Okay, so we're not going to be talking so much about the mobile push, although, well, yeah, we kind of do cover that with Kafka a little bit, but well, yeah, it's not core. What about more up-to-date information? The most up-to-date information I found was from 2017. So I searched last year for, and it's essentially these companies don't really tell you all that much, yeah, because it's part of their, I don't know, their IP or whatever, how they're processing data. They do, however, sometimes release software, or they sometimes develop software that gets released open source, or they release white papers about the systems they use. So we see more or less that some of the main aspects are still in use, but essentially there's very little information available about that. So they've updated some of the components to use more modern software. Okay. Let's have a talk about the first lab. We're going to have a lab on Wednesday where we're going to talk about, every Wednesday in this course, I'll talk about the structure a little bit later. We're going to have a lab. So you come here, you work in your laptops, and you'll try to solve some tasks. You're going to try to address some tasks. We're going to start with a relatively simple task. You'll have all the source code, and mainly you're just going to play with this idea. And the idea is just using your own machines. If you can bring machines, that would be great. How good is your machine at processing data? How fast can it process data? What kind of data can we process in it? What happens when we can't process anymore? What are the other options, right? So we're going to be looking at the trade-off between in-memory and disk processing, using your disk to process data versus processing it all in RAM. What we're going to do is take a dump of a surface version of Wikipedia. It has the first paragraph, I think, of every article in Wikipedia. So it's a big chunky text file. Yeah, it's not massive, but it's big. So if we wanted to find the most frequent words, which words appear the most, how could we do this? I give you a text file, it's probably about 500 megabytes compressed. You don't probably want to decompress it, it's large. And I ask you, give me a list of the top 10 words. I think it's Spanish Wikipedia. So let's say I want to improve my Spanish and I want to know what are the top 10 most frequent words appearing. How do you do it?
I don't want to, but I'm gonna read them.
Hmm?
You're gonna read them? You're gonna read everything on these ones.
Yeah, you have to read the entire file at least once. Yeah. So what do? You open the file. Let's say we open the file. Let's say we open it and we can stream directly the compression, right? So when we open the file, we can start reading it.
I create a dictionary and I will watch each word.
Yeah.
And if the word exists in the dictionary, I put one of them.
Okay. Yeah.
And else I put a new word in this.
Okay, perfect. So use a dictionary, use a map, right? So something like this, right? You have a file input and your input is your input file in K, which is I want top 10 or I want top 100, right? You have a map or you have a dictionary. Yeah, you go through it and you say for every word in the file, I'm going to skip the parsing, but let's assume that as we read it, we break it up by spaces. It's not very difficult, right? For every word in the file, I'm going to get the count of that word from the map. If it doesn't exist, I'm going to put in the word in 1. If it does exist, I'm going to put in the word and the value plus 1. Yeah. What language would you use for that? In what programming language? You said dictionary, so Python. So yeah, there's a big difference. But yeah, okay. So afterwards, we have a slightly tricky thing here, which is we still need to find the top 10, right? So the easiest way would be to sort by count your dictionary and then take the top 10. Yeah, or you can handle, ties and so forth, right? So what's the issue here? Memory. How big is your dictionary going to be? Will it fit? You have to come on Wednesday to find out.
Well, technically, yes.
You think so?
The dictionary is just this thick.
I'm not sure. I think in this case, well, I mean, it's
Dictionary, words are limited.
so, but in this case, if you had a dictionary, I mean, your intuition is correct. So I don't want to give away what happens on Wednesday, but it's not a dictionary, it's Wikipedia. And Wikipedia contains lots of names of things. So they will be words too. Right? So it's not just your dictionary, but we'll have to see. Yeah. In any case, even if it does work, I'm going to give you something harder until your machine breaks, until there's no more memory. Yeah.
Oh, thanks.
So no problem. You're welcome. So, okay. So in fact, we could expect that if it were just the dictionary, like the dictionary itself, there aren't that many unique words. Yeah. And there is this thing called Heaps law, where we have, as we read into a very large document, like I'm going to give you, the number of unique words that we see will reduce. The rate of new words that we see will reduce because we've already seen so many, right? This is known as Heaps law. So as we read further and further in, if it were just the Spanish dictionary, we could expect that it would be fine with a gigabyte of memory or something like that. But we'll have to see what happens with Wikipedia. If the words or the phrases or whatever don't fit in memory, what can we do then? We have to use the hard disk. Yeah. Exactly. No, it's going to be a lot more complicated. So why is it more complicated? We already have our code, right? And we say, okay, instead of keeping this map in memory, we use disk. It's still ones and zeros. Yeah. We can even, we can do this various ways with swapping or whatever, but whatever, our memory mapping. And we're going to do this part on disk as well. Any problems? Would it work just to run the same thing on the disk? Time. Why is time going to be bad? There's a certain thing we saw earlier with the data access. It's the latency of the hard disk, right? So can we do the same storing the map on disk? Yes, but we're gonna have to wait a very long time. Yeah. So here, and here we have random access. And if we do this as we would do it in memory, there might be random accesses here as well. Random access means we're going to jump to some part of the disk, to some location that's not sequential. And how long does that take? It takes around 10 milliseconds. That's the latency we saw in the other part. Why does it take so long? Because we have a mechanical arm that has to move to the right place. So it takes time for this mechanical process to happen. It takes about 10 milliseconds for the disk arm to move if you have a traditional disk. If you have a solid state disk, things are not going to be so bad, but it's still going to be orders of magnitude slower than what you did in main memory, right? So if we wanted to do 1 million seeks, if we had a word count of 1 million in a file, it would take 3 hours just to do the seeks. Well, you need even more because you probably need several seeks per word, right? So it's going to take a long time. So when we use the disks, hard disks, what we want to do is we want to use sequential access. We want to reduce the number of random accesses. We want to reduce the amount of jumping around on the disk that we do. It's not so bad in RAM. It's terrible on a disk, even on a solid state disk. It's not good. Yeah. So could we count words and phrases? When I say phrases, that's how we're going to make it difficult. Rather than getting you to count words, you're also going to have to count n-grams, which are sequences of 2 words or 3 words or 4 words. And we'll keep increasing n until your machine breaks and then you have to find another solution. How could we do this without all these random accesses? How could we count the words in such a file without using random access? Any ideas? It's nothing like what we were doing in memory. So we're not going to jump around on disk anymore.
You could sort the file before processing it?
Yep. Yep, we could use sorts. So we need to pre-process a little bit, right? So we need to somehow take the words in the file. Here they're delimited by line, in the file they'll be delimited by space, but we can manage that. What we're going to do is order or sort the file. So if we sort the file, this very strange file, we get an idea of how we can start to count the words now, right? We might have to apply some normalization if we want, like lowercase, remove the tildes and whatever, right? But hopefully get the idea. If we just read this sorted file once, how much memory do we need? We just need to store the count for the current word. Yeah, so we need to store a word and a count, a string and an integer. Yeah, and we can detect when the word changes, update, print out the old count and the old word. Yeah, so we don't really have any major requirements for memory. Here we see that process. Yeah, so when we read here, we load k into memory with 1, and we see here, here's k. We compare it, we say it's still the same word, 2, k2. We read here, we say, oh, what happened to my pointer? We say, we have k2 in our state, and we see k again, same word, k3. Yeah, we read here to tan, and we see that it's a different word, so we print out k3 and we put tan1 into state. Yeah, and that gives us this here. Does that make sense? Okay. And finally, we can order by occurrence and take our top k. How can we order the words on disk? How do we do a sort then? It would be fairly easy if we could load all of the words into memory and then sort them in memory, right? You learned all the bubble sorts and the insertion sorts, and or many of you have, not all of you, but there's various ways to do this, right? Quick sort and whatever. There are various algorithms for efficiently sorting stuff in memory. But we don't, the data won't fit in memory. If they did fit in memory, we just do the first thing, right? We just have a dictionary and count and it would be fine. So how can we order large files on disk with limited main memory?
We can like chunk this and order like sort this. We insert in memory, yep, and then we merge those.
Yep, perfect. Yep. So the idea is we're going to sort batches, chunks of the data. So we're just going to read a chunk of the data in. We're going to define here a size of n. We can also detect maybe when we're filling memory. There's other ways to avoid defining it, but the most reliable is just to define, okay, we'll read n things into memory, right? So we have a batch of size n, in this case about what, 12 or 13, don't know. We read it from the disk. We order it in memory. Sorry, the batch in this case will be of size 4. Yeah, so we have 4 elements. We read them into memory, we sort them, and we write out a batch. And each batch is sorted. Yeah. So we continue, we read the next batch, we sort that in memory with quick sort, for example, we write out the batch. Yeah. So we continue in this way until we have 3 sorted batches. Yeah. And then we need to do a merge sort. Yeah. So the merge is not too complicated, but not too easy either. Yeah. But what we need when we do the merge is we just need to keep a pointer in every batch. And we need to keep some sort of list in order in memory. And what we're going to do is we're going to find out which is the lowest line, so far the lowest element in some of the files. And we also have the ID of the file it's from. So the first thing here is a CS. And we have Della and Della here. So we read a CS. Yeah, it's here, ordered. So we're going to write a CS, and we know it came from file 3. So what do? We read the next element from file 3. Yeah, so we move the pointer down to file 3, and then now we see we add Della with the ID 3 here. We see we have a tie. Let's just say we break the tie based on file ID or whatever, it doesn't matter. We read Della 1. What do? We read from 1 again. Yeah. So we read always the lowest item in the order. We see what file that was from. We write it out, and then we read something from the file again. So we always maintain one thing from every file in memory. Yeah. Es que ha sido, and we keep going like this. Yeah. And we're almost out of time, so I'm just going to fast forward that part there. Do you understand? If not, I can also go through it in more detail on Wednesday. Yeah, we'll be talking about this. Okay. So once we have the data sorted on disk, yeah, we've already seen the count, right? So if we want, we can then order again by frequency, right? This is still ordered by alphabetical order on the words. We can apply the exact same external sort. This is the name for this process of breaking a file down into batches, sorting the batches, and then merge sorting those. Okay? An external sort. So what about scaling further? If our one machine isn't sufficient, we could consider using n machines. And that's where the second part of the course comes in. So any questions or doubts? About the course, briefly, data intensive, not compute intensive. We're going to be talking about distributed tasks, not networking. I'm far from an expert on networking. I guess people here who took networks would know a lot more about networking than myself. Commodity hardware, not supercomputers. We're not talking about these craze or the supercomputation type frameworks. We're also not going to be talking too much about GPUs and so forth, because although they're very useful, it's a different type of processor. It will be another course. General methods, not specific algorithms. So we're going to look at specific algorithms in the context of labs, but it's more as just examples. I really want you to kind of be able to think computationally about how to distribute tasks on multiple machines. That's the main goal. And we'll see some examples of specific algorithms, but it's not the algorithms that are interesting, right? Practical methods with a little theory. Actually, there's very little theory. Mostly it's hands-on experience with the frameworks that are most commonly used. Distributed computing, brief introduction, 1 week. Distributed processing frameworks, about 5 weeks. Information retrieval, that's about search engines, searching text and so forth, 2 weeks. 3 weeks of distributed databases, where we'll mainly look at NoSQL stores. And projects. So course structure, Monday lecture like this. I'll teach a new topic pretty much every week. Some will be continuations, but in general, it'll be a fresh topic every week. Wednesdays, we have labs. So this Wednesday, we'll have our first lab. So if you can bring, the most important thing would be if you can bring your notebooks, that would be great. You can work in groups if you attend. If you can't attend the session on Wednesday, you can work alone. You can work in groups of up to 3, because that's easy for people sitting here to work in groups of 3. 4, it's a bit too wide. So it's important that there's at least 1 notebook per group. We used to be able to borrow notebooks, but since the pandemic, they were lent out, and I don't know if they came back. Last year, they weren't available, but I'll try to see if there are notebooks available. I'll try to have that. Friday's auxiliary. So you can use that for Q&A, resolve doubts, to continue working on the projects, essentially. I forgot to update here. This isn't live yet, so I have to update this, but I'll post in the forum afterwards. I will update all of the slides, or put all of the slides online and make them available. Course marking, 80% for weekly labs. So there will be 11 labs in total, and the best 9 of those will count. Yeah. 20% for a class project. Yeah. So bad news, assignments each week, working in groups. Good news, hands-on each week and working in groups. Okay. So as you prefer. Outcomes, we'll learn more about this area called big data. You'll learn about aspects in practice such as fault tolerance, distribution, distributed computing, and we'll get hands-on with many of these frameworks you see here. And also learn how different web companies manage their data, and how like Twitter and Facebook and Google are.
Which language we are gonna use?
Yeah, so this is an important question. We can't use Python. We can't use Python. So mainly the main language will be Java. But I know that some of you don't manage Java. So we're going to give some help, some tips for that. I think it's great to, there are some cases where you can use Python, but Python is just not efficient enough for big data. It's too inefficient. It's the Java police are going to get me. Most of the big frameworks are written in Java. We know, so if you're really like don't know Java or whatever, and you want to take the course, you're more than welcome. We're going to help with that, but a bit of Java will be required. Yeah, but we're going to give help. Python is not an option in practice. And I can explain more about that later if you want, but it's an interpreted language. It's too efficient, too greedy for memory and so forth. But there are other options sometimes where there's interfaces that can be compiled into something.
For example, in a work, in my job, for example, what language you recommend?
It depends on what kind of work you're doing. If you're into machine learning kind of stuff, you can get away. I mean, you can do almost everything with Python. There are options for Python for what we'll see. There's options like PySpark, but in general, they're added components because these frameworks themselves are not written in Python because they can't be interpreted. It's too inefficient. So they're written in C, C++, Java, Scala, these sorts of languages. So in general, Python is okay for machine learning, but not for this type of work. Other questions? So there's about 5 labs, I think, in Java, and the rest are using custom languages. And we'll help you with the job. Yeah, we understand. Any other questions? So I'll post soon on the forum some instructions about what we'll need for Wednesday. And see you on Wednesday.
Ciao, ciao in Zoom.